Hello everyone, thank you for joining our lesson today. Before we move on to today's topic, let's go through the solution to last week's problem. So I gave you a travel graph, just like this, and your instructions were to describe what is happening at each stage of this travel graph. So let's have a look at stage 1 first, okay? There are 5 stages, 1, 2, 3, 4, 5. First thing we have to notice about a graph, we need to look at the labels of the axes. So the x-axis is time and the y-axis is distance. So let's look at number 1. From 0 to 20 seconds, the car has gone all the way to 100 meters. Okay, so we can say the car is accelerating here. The car is moving, traveling to 100 meters. And in stage 2, for 10 seconds, there, that part from here to here, the car stays at 100 meters. Therefore, stage 2, the car is standing still. Okay. Time is going, but the distance remains the same. Same distance, right? Stage 3, from 30 seconds onwards to 40 seconds, I believe. Yep. The car travels another 200 meters. So here in stage 3 here, the car has gone, in 10 seconds, it went an extra 100 to 300, it went 200 meters. So it's going even faster than stage 1. In stage 1, it was going 20 seconds, it went 100 meters. Okay? Notice that the gradient, remember we talked about the gradient or the slope? So this one has a flatter gradient, flatter than stage 3. Therefore, 3 is traveling faster than stage 1 here. Okay? Higher gradient, a steeper line, means it's traveling faster, the car. Stage 4, what is happening at stage 4? We see that for how many seconds is this? From 40 seconds to, what is this? 90, how many seconds is that? 95 is it? I believe. Am I right, Samina? What do you think? Where does that line up exactly to? 95 seconds, or somewhere around 100 or 95 seconds. Let's just put it at 95. So, see how long, for that whole period, from here all the way to here, the car stays still at 300 meters. So again, similar to point 2, where the car is standing still, on point 4, stage 4, the car is also standing still. So 4, the car is standing still. The car has stopped, basically. It stopped moving. So time is going, but the distance is the same. Notice the flat line. Okay? This graph is sometimes referred to as a DT graph, or a distance time graph. And finally, stage 5, look what happens. On the distance y-axis, the line goes down. So what that means is the distance is decreasing. Okay, time is still moving forward from here to here, but the distance is decreasing, which means what is happening at stage 5? The car is moving backwards. So from the original point, the car went all the way 300 meters over here, and then it's coming back. So let's imagine this is the car. It went all the way 300 meters. And then over here, from that stage, it's going backwards that way. Okay? And it goes all the way back to the beginning, 0. So it comes all the way here, and then after 120 seconds, it goes all the way back to the starting point. Okay? Okay, our topic for today, integration, also known as integral calculus. And our topic today, we'll be talking about the indefinite integral. Okay, it's an introduction to the indefinite integral. Let's look at our key terms. So our key terms for today on integration is integration, the antiderivative or indefinite integral. Okay, they have the same meaning. The definite integral, powers or exponents, a possible constant. Okay, the key word there is a constant. Constants in maths, they're usually denoted by C. Okay, the letter C. Theoretically, what does theoretically mean? And range, or sometimes called boundaries or limits. And here are some instrumental mathematicians who helped out with the field of calculus, or the discovery of calculus, Newton and Leibniz. So, an introduction to integral calculus. In our differentiation presentation, we used the tangent and velocity problems to introduce the derivative. Remember when we were talking about differentiation, we showed graphs and we showed the tangents. Okay? It's all about differentiation. So these things, tangents, and we also dealt a bit with the velocity problems, like we just did in the beginning of this lecture, the solution to last week's problem. So those kinds of problems, these are central to the idea of differential calculus. In the same way, this field, integral calculus, uses ideas of areas under curves. So a lot in what we talk about in integration, areas under curves. What's the area? Okay. In much the same way, this field uses ideas of areas under curves to formulate the idea of integrals. Okay, in differentiation we talked about a derivative. Now, basically the opposite, we're talking about integrals, which is a basic concept of integral calculus. There are two types, indefinite integrals, or also known as antiderivatives, so it's the opposite of a derivative. Okay, hantai, opposite. And the other type are definite integrals. And these use limits or boundaries. More on that later. So today we will be dealing with indefinite integrals. What is an indefinite integral? Let's move on. So, differential equations. A differential equation is an equation that contains a derivative. For example, this is a differential equation. Okay, remember before the past few weeks we've been talking about differentiation, f dash or dy over dx. So let's have a look at this. dy over dx is equal to 3x squared. Now, when we are integrating, or also known as anti-differentiating, we are basically doing the reverse of finding the derivative. So the integral of 3x squared is x cubed. Okay, so just imagine this is f, and that's f dash. Remember, x3, when we're finding the derivative, the dash there, take that 3, put it in front of the x, take away 1. Okay, so we got that. And all we do in integration is go back the other way. Let me go further with this. Okay, so the antiderivative, or indefinite integral, an antiderivative of a function f is a function capital F such that f dash equals f. What does that mean? Have a look here. An example, an antiderivative of fx equals 6x. So, what do you call it? The integral of that is, of capital Fx is 3x squared plus 2, since f dash x is equal to fx. So, for example, if we find the derivative of this, 3x squared, remember what we did before in the previous sessions? 2 times 3, this would equal to, so f, that's f, function f. Now, function fx, remember the rule? 2, 3, x, 2 take away 1, plus 2. Now that cancels out. All constants become 0, the constant rule. 2 3s, 6, 2 take away 1, 6, x, x1, or just 6x. Okay? So this is 6x is a derivative of this function. Therefore, the integration is going back the other way. So the integral of this value, 6x, is 3x squared plus 2. The antiderivative or indefinite integral, again, this is how we write the expression, okay, elongated function of x dx. So this, you read this as the indefinite integral of f with respect to x, similar to differentiation. So it means to find the set of all antiderivatives of f. Here's the integral sign, so stretched out s. Okay, this is the integrand, this is the function here, and dx. X is called the variable of integration. So you can have an x, sometimes you can even have instead of the x's, you can put a t or an r, any variable, any letter. Let's move on. The constant of integration. Every antiderivative, capital F, of f must be in the form fx is equal to gx plus c, where c is a constant. So notice from our example before, remember we're going, instead of going that way for differentiation, we go this way for integration. Okay? So what do we have here? This represents every possible antiderivative of 6x. So what's the rule? How do we get from 6x to 3x squared plus c? Okay, what's the formula? Okay, this is integration. Again, remember that's differentiation. To go back the other way. Our key rule, and this is our key formula, it's the power rule for the indefinite integral. Okay, basically the formula is xn plus 1 over n plus 1. Okay, notice that n is the exponent or power. Okay. Look at this example right here. So differentiation, elongated f, integrand x3 dx. So x3. Notice also that this x refers to this variable. So if this was 2x3, this x would be the whole 2x. Okay? That term right there. Go back to our x3. So let's use this formula. N is 3 from there. Okay, we can see the 3 is n. So x, n plus 1, 3 plus 1, over n plus 1, 3 plus 1, equals to x to the power of 4 over 4. Okay, oh, don't forget to add the c, the constant. We'll talk about that shortly. What is this c here? That can also be written as 1 over 4 x4 plus c. Okay, that's the same as that. Now, what is this plus c? So c, the constant, what is that? Remember from our differentiation lesson, the derivative of a constant is 0. So, for example, if we have 3x squared plus 5, that's a coefficient. This is a variable, the x, that's a power or exponent, and this is a constant. Okay? Notice that the constant does not have a variable. There's no x or y. So this is a constant. And when we find the derivative of that, or say the dy over dx, or f dash, if that's fx. So if we find the derivative, it'll become 6x, and that'll cancel out, that'll become plus 0. Okay, so it just becomes 6x. So notice that we're missing that plus 5 here. So in integration, when we move back, this will become c, plus c. It represents the constant. When you integrate, you have to take into account that there is a possible constant. What is that? Kano? A constant involved. So theoretically, a differential equation has infinite solutions. Now let's have a look at these examples here. We add the plus c when we are integrating to show that there may be a constant. Okay, have a look at that example. Notice that all of these use the formula xn plus 1 over n plus 1. Let's go through this one right now. 2x to the power of negative 3. So we take our x will be that, and our n is negative 3. So 2x, negative 3 plus 1, over negative 3 plus 1 equals 2x, negative 2, over negative 2, 2x, negative 2. That can, negative 2 can become negative 1. So negative 1, x to the power of negative 2. So negative x to the power of negative 2. Negative x to the power of negative 2. Okay. What's another way of writing this? Negative x to the power of negative 2. You can write it as negative 1 over x to the power of 2. Right? Okay. Let's move on. So, today we had a brief lesson on the indefinite integral. Here's a practice question I'd like all of you to try. Try this at home. Integrate 2x plus 5 to the power of 3. Okay, so don't forget to expand it first and then work on each term. And thank you very much for viewing today's lesson with Everyday Seminar. Hope to see you next time.